Alright, let's do it. Let's do it again. So this time we continue with our story on derivatives. One of the cornerstones of the entire calculus course. It handles the slopes of functions, slopes of graphs of functions, and it handles them very elegantly. And that's where we're at right now. We'll backtrack just a little bit. We start off with a secant slope, slap a limit on both sides, changes it into a tangent slope. We ask the same question, not at some point 2, but at some point generic point C. We got formulas for all these and more, and you did that for homework. We're piling up a list of famous things we found out, famous derivatives of famous functions. We continue that list last time. And we started doing properties as well. Pulling the constant before you take the derivative, pull it out, leave it out of it. We talked about how to handle the sum of functions. Derivative of the sum is some of the derivatives. The product rule, super famous. I think we proved that last time as well. And what we want to do is expand on this. Expand this list of famous derivatives. We want to expand this list of famous properties. We want to add a couple more today, the chain rule and the quotient rule. And maybe we want to expand on the notation. All this time we've used the prime to denote finding the formula that gives you the tangent slopes at every point. We want to expand that. We want to introduce this new notation, which is, well, new for us, but it's really, really important and famous. It's the denotation. It's called df dx. This will become incredibly important. Sometimes people write it as dy over dx, because often people write f. The f function is a y function, commonly used on the axis, either the f or the y. That's what we want to do today. Again, we want to expand the list of famous things. We want to expand the list of identities or properties, and we want to introduce new notation, the denotation. Very, very powerful stuff. Okay, so where to start? Where do we start? Started there. Alright, so let me explain the notation. Before we would have just written brackets here with a little prime to indicate that we're going to do something to the function. We're going to find its formula, its avocado tree, its derivative, the formula that gives you the tangent slopes at every given point x. And so we would prime it, and today we have a different way of saying it. Instead of priming it, we ddx it. This ddx thing will become a verb. It's a verb that you do to whatever's in here. You take the derivative of. Same thing as the prime. The prime was a verb. You take the prime of whatever's in there, you find its derivative. Okay? This time, and it's always customary to put it on the left-hand side. I know if you're a beginner, sometimes you may be tempted to put the dx. Let me erase that. Some of you guys may be tempted, if you haven't been doing this for a long time, to put the ddx over here. That's just weird. No, people don't usually do that. If you want to be weird and do things differently, you're one of two kinds of people. Either you're a trailblazer or a lost soul. So if you want to be just a standard kind of person, you want to put it on the left hand side. This is the way we do it. It's a verb. You take the ddx of whatever's in there, and often once you do that, you put the thing on top. You say, okay, well, that's ddx of star, and you put it as a quotient, and most of the time it will look like this. Before, it would look like f prime of x, some formula. Now it looks like df dx. It's still some formula, but we have a different way of denoting it. Much more powerful, by the way. Not as simple. We give up some of the simplicity, but we gain a lot of power through it. Also, sometimes people just write dy dx. Instead of f, you could replace that with y, usually, depending on the function f and whether you're calling y equals f. Also, before we would plug in an actual number here, 5, you wouldn't get a formula anymore, per se. What you would get would be an actual number, which would be the tangent slope. This would be the tangent slope of the graph at the point x equals 5. The way it would look like over here is this weird little notation. They write the df dx, which is some formula, then you write a little slash here, which is meant to be evaluated at x equals 5. So this thing right here means exactly the same as that whole thing. I know the notation in some places it looks more clumsy. This looks a lot more clean and elegant. This looks kind of clumsy, but believe me, this one has its day when, or it's places where it's a million times more powerful. Okay, so that's a different notation. Maybe we can do a couple of the problems that we did before with a prime notation. Let's do it with a ddx notation, just so we can get a little used to it and not be so afraid. So before we would have done it with a prime and we would have said, okay, the derivative of that is 12x to the third, whatever. Today we do it slightly different. Today we do a dx. Very often it's read the derivative with respect to x of 3x to the fourth, and that would be equal to, you're doing something. It's a verb that you're doing to this thing, to the function. You're finding out its formula that generates all possible tangent slopes. That's how you do it. Okay, this is a standard way. I think you need to get used to it. It's very, very important that you do. Before we would have just taken the prime. Today it's almost the same thing, except we use a different notation, ddx. We ddx, take the derivative with respect to x of 7x squared, and that would give you 14x, just like that. See, it's important that you get used to the d notation. The derivative with respect to x of 5 sine x, that would have been, you keep the 5 out of it and you just find a derivative with respect to x of sine x, and that would be 5 times the derivative sine would be cosine x, and you're done. Similar as before, we're just practicing a new notation. D dx of 9 ln x is equal to, again you pull out the 9 and you have d dx of ln x, and that would give you 9. The derivative of ln x with respect to x is just 1 over x, and so you get 9 over x, just like that. These are famous derivatives, by the way. Oh, you got to be good with your famous derivatives. Maybe one more with the sigma, with the d notation. So you suppose you have d dx of x to the third plus x to the seventh. Well, that would be d dx of x to the third. I'm going to do that separately, and d dx of x to the seventh, and that would give you the derivative of x to the third would be 3x squared. The derivative of this would be 7x to the 6, and you'd be done. Okay, it's not too bad, but I still haven't shown you the power of the denotation. The denotation is super powerful. Let's review real quickly the product rule. This would be a good review. You would write x to the third times x squared plus x to the third times x squared. On the first one you do d dx only of the first piece. On the other one you do d dx only of the second piece, and you leave the rest of it out of it. And that would turn into, of course, 3x squared times x squared plus x to the third times 2 times x, for a grand total of 3x to the fourths and 2x to the fourths, for a grand total of 5x to the fourths. Alright, that's just a little taste of the denotation. I do think it's incredibly important that you do a lot of homework problems and become extremely comfortable with the denotation as well as with the prime notation. And just wait for the rest of the story. I can't tell you everything at once, but soon we're going to try to see why this is incredibly powerful. Well, let me give you just a little tiny little glimpse at why that would be powerful. Let's skip these. If you look at the graph here, before we would take a tangent line, say something like this, and say, all right, if I wanted to find the slope of that line at some point here, c, well, the slope is equal to f prime of c, which is all right. That's an okay notation. That's what we did before. Consider that, compare it to this notation. which is a lot more, it tells a lot more of the story. In this notation, we consider this line, the tangent line, and then we consider making a triangle out of that, where that's the hypotenuse, and we consider denoting the change of y. This is a small little tiny change of y, often denoted by little tiny dy. Dy means a differential. It's a little tiny, you can think of it as a little tiny change of y, an incredibly small change of y. And this part right here would be an incredibly small change of x. And so if you wanted to find the slope of this line, another point of view besides this one would be, hey, the slope would be the dy over dx. The incredibly small tiny little increment in y as compared to the incredibly small increment in change in x. And that's not the whole story, but this is certainly a big part of it. That's why this notation becomes a lot more useful. It tells you a lot more than just f prime of c. It tells you which variables are changing with respect to what, dy over dx, where this one is just, you have to assume that the prime is with respect to x, and that you have to assume a lot more. So that should get your mind going in the right direction, and we'll have more about this story later, but you know, Rome wasn't built in a day, so gotta take it easy. Alright, today we're only doing a few things. We're doing the new notation, we're doing a couple of new properties, the chain rule and the quotient rule, and hopefully we'll learn a couple more new derivatives. It's an easy day, easy as Sundays. Drink your lemonade. Okay, easy day today. Anyways, incredibly important. You guys gotta do the homework and get used to the denotation. Very similar to the prime notation, but 1,000 times more powerful. Maybe slightly more complicated, but you give up the simplicity, but you get a lot more power in return. Alright, so that's the intro to the new and improved notation for derivatives. Let's change gears a little bit to the infamous, world-known chain rule. So let me try to explain it this way. By the way, you should do so much homework on the primes and the ddx's that you should become fluent in both. If I write primes, you should know, you should roll with it. If I write ddx's, you should roll with it just as well. It's incredibly important. It's imperative that you become comfortable with both notations. Let's just do primes now for now, and maybe we'll interchange as we go on. The chain rule goes something like this. It handles the situation when you have f of stuff, and what I mean by that is we have done things like the derivative of f of x. We've done things like that. That right there, you can say check. We've done that, but we haven't really done many where you have f of stuff. Where you don't have an f, you have f instead of having. Where you don't have an x, instead of having x there, you maybe have 2x plus 5. That right there, that's what I mean by stuff. That looks a little bit different. How do you take the derivative of that? F of some other stuff other than x. The chain rule is tailor-made to handle exactly this situation and a million other situations that have the same principle applied to it. It is perhaps one of the most important properties or rules for the derivative. You see, by the end of today, if we master a chain rule, every single derivative in the entire book, you could grab that big, thick, fat calculus book with 2,000 pages, you will be able to handle every single one of those by the end of today. It's all in the chain rule right here. Amazingly, huh? Amazing. So let me tell you how it goes. The chain rule says if you've got f of any sort of stuff, what you do here is real simple. By the way, there's always a few important questions. One is, what does it say and how do you use it? And second is, how do you prove it? We'll leave the other one for last, but let's at least first learn what it says and how to use it. It says that if you've got the derivative of f of stuff, all you gotta do is figure out the derivative of f, evaluate it at this stuff, and then you add stuff here, prime. Amazingly, that's what it says. Let me give you an example. I'll compare just a regular one, x to the third. If you had to take the derivative of that, you would just do 3x squared and you'd be done. However, if you had to take 2x plus 1 to the third and you wanted to take the derivative of that, well, the chain rule is tailor-made to handle situations like that. It says, hey, don't worry about the stuff in there. It's just 3 times 2x plus 1 squared. You see, that's exactly the same thing as we did before. However, the chain rule says because you weren't just dealing with x, you were dealing with some other stuff, you got to add on the derivative of the stuff here at the end. The derivative of 2x plus 1 prime, which would be equal to 3 times 2x plus 1 squared times the derivative of 2 x would just be 2, the derivative of 1 would be 0, so it's just times 2, just like that. See how that works? Anytime you have for any sort of thing in here in the middle that's not x, you're gonna have to add the stuff prime at the end. That's what the chain rule says. Let's do that again. Suppose you had let's move this out of the way. Let's do a square. Suppose you have 3x plus 5x squared, and you had to do that to the 7th. What you have here is some stuff to the 7th power. You would do it the same as you've always done it. 7 times 3x plus 5x squared. That's what we've always done. That's called the power rule. You bring this one down and you subtract 1 from it. The chain rule says, wait a minute, you're going to get it wrong because you're not really just dealing with x, you're dealing with some stuff in there. So what you've got to do here is add the 3x plus 5x squared prime. And then you'll be correct. Then you'll be good. So the grand total would be 7 times 3x plus 5x squared, all to the 6, times the derivative of 3x would just be 3, plus the derivative of 5x squared would be 10x. Just like that. See? Pretty easy, huh? But the possibilities are endless. For example, we've done the derivative. For example, we've done this: the derivative with respect to x of sine of x. This is old news for us. We've done this many times. The derivative of sine would be cosine of x, the super famous one. What we've never done is a derivative with respect to x of sine of some other stuff. What if I put some other stuff here, like ln x? Ooh, chew on that. That, my friends, that's a totally different issue. It might look incredibly complicated, but the chain rule makes child's play out of it. It says, you know what, don't worry about this stuff. It's all good. This will be the cosine of the stuff, ln x. And if you stop there, you're going to get it wrong. The chain rule says just add up the stuff prime, ln x prime, and then you'll be good. That would give you a total of cosine ln x times the derivative of ln x would be 1 over x. And you could actually nest these, like nest 5 or 6 of them. You could have sine of stuff, ln of stuff, stuff of stuff all day long. You just have to keep multiplying it. It's like peeling an onion. See, this kind of stuff we've done before. The derivative with respect to x of 10 to the x to the 10th, we've done that stuff before. This is famous. It's called the power rule. You bring down the 10, that gives you 10. Then you leave the x there and you take 1 unit away from the exponent, so that 10 minus 1 it would be 9. We've done that stuff before. That's child's play. What we've never done before is something a little bit more interesting, such as sine of x to the 10th. That one we've never done. But the chain rule says, no worries, this is my domain. It looks like 10 to something to the 10th power, so all you do is you take the 10 and you do sine to the 9th of x. Okay? And that's pretty much it. Not. Yeah, if you stop there, your conscience should feel a little bad, like you're doing something wrong. It would be fine if it was x to the 10th. You're doing the derivative with respect to x, but you're doing sine, so the chain rule says always add the stuff here prime. That's what you have to add, the stuff prime. So this would be 10 times sine to the 9th of x times, and this would be cosine x. And now you're done. You may wonder, well, why weren't we doing that before? And in fact, you could think about it this way. We were always doing chain rule. Even if you just have the derivative, so this, I'm going to go with prime for now. X to the 7th prime. You say, well, that's 7x to the 6th, right? But then you got to do x prime, the stuff inside. Yeah, you have to. You always do. That's chain rule. But then 7x to the 6th, what's the derivative of x? The derivative of x with respect to x is 1. That's why you never saw that. That's why it looks like we stopped there. But really, you're not supposed to stop until you're down to 1. It's like peeling an onion. Well, we can try one where we nest a couple things. Let's clone it. Let's do... What do you guys want to do? Something crazy. You guys getting the hang of it? Let's do ln of sine of x squared. Yeah. Can you do that? Oh, the chain rule is big time. It's big time. You could do anything. Anything on that big fat book you could do. With a little audacity, some lemonade, and the chain rule. What's the derivative of ln of any stuff? You could even do it here on the side. I'm going to have a summary sheet. If it's not up yet, it will be up soon. A summary sheet with all the chain rules for all the famous functions. One of the entries there would be, anytime you have ln of stuff, I don't care what the stuff is, if you want to find the derivative, what you do is you go 1 over the stuff times the stuff prime. That would be one of the entries. I don't know if you can see it there. ln of stuff will be 1 over the stuff times the stuff prime. So if you have ln of a, for example, and you wanted to take the derivative, it would be 1 over a times the a prime. That's exactly what we have here. We have ln of stuff, so it will be 1 over the stuff, which would be sine of x squared, times the sine of x squared prime. And that's pretty good, but you can still do more work over here. 1 over sine of x squared. Let me think. Sine, here I have sine of stuff. I don't just have sine of x. No. If it was sine of x, okay, it'd be real simple. But it's sine of some other stuff, so I gotta do cosine of that stuff times x squared prime, times that stuff prime. And that would give you 1 over sine x squared times cosine of x squared times 2x. Just like that. Okay? Super famous chain rule. You could do everything on that book using the chain rule. It's like an onion. Just do the outside, ln of stuff, then do the stuff, then do the stuff inside the stuff, all day long. Alright. But I think I should stop here for the enough examples of the chain rule. These are just little baby examples to get us started. Maybe I do one more. What the hell? How would you do cosine of x to the third? By the way, a lot of times people don't write it that way. It really means cosine x to the third, but people will usually write it with a 3 right there. You should know that that means the same thing. What if you wanted to take the derivative of that thing? Well, it looks like some stuff raised to the 3rd power. Something under my finger raised to the 3rd power. So how do we handle that? Well, it's 3 times that to the 2nd times that prime. So it would be 3 cosine x squared times, this is the one we haven't done before. It's actually a negative sign. Well, maybe you have done it for homework. Anyways, I think we had enough of these little examples. I want to change my attention still to to chain rule, but I want to change my attention to some timeless derivatives. I told you that this thing will get you all the derivatives in that entire book, more or less. So I want to turn my attention to some of those super famous ones, so we can expand our list of famous and well-known derivatives. For example, what's e to the x? Ooh, I don't know if I want to do that one now. Secant to the x. What's a derivative? Ooh, cosecant to the x. What's a derivative? Ooh, tangent x. What's a derivative? Ooh, e to the x again. Ooh, quotient rule. Oh my goodness, we got a lot of timeless ideas. Ooh, I just thought about another one too. Let's put it here so I don't forget it. How about this one? That's the derivative of arctangent. If your y function is tangent inverse of x arctangent, then what's the derivative? Huh? What is your dy dx equal to? Take that. Oh, super famous, timeless. The derivative of arctangent function. You guys have seen it, right? The graph goes something like this. If you haven't seen it, you can always plot points. That's more or less what the graph looks like. And you want a little formula that at any given point C, boom, it'll tell you this tangent slope of the line, that graph. Nice. You can do it. Guess how? Chain rule. It's all about the chain rule. Today's chain rule day. Alright, which one do you guys want to start off on? Let's start off on this one. This one looks to me like, we can do it this way. Secant is 1 over cosine. So it's cosine of x to the negative 1. Yeah? That stuff in there. Here, maybe I should do it in a different color. This is just the prime stuff. The stuff inside secant is the same thing as cosine raised to the negative 1. I don't mean arc cosine, I mean cosine raised to the negative 1 power. Don't confuse the two. And I write it this way because this way I can apply the famous chain rule. I got blah to the negative 1. I have stuff to the negative 1. This is just power rule. So the derivative of that would be negative 1 times that to the negative 2 times the stuff here prime. So it would be cosine x and then cosine x prime. This would be equal to negative 1 over cosine squared x. That's again, it's an exponent. The root of cosine would be negative sine x. Negative becomes positive, so all I have is 1 over cosine x times sine x all over cosine x. I wrote it this way because it's famous when you write it this way. Instead of writing the cosine square here, I separated it into the cosine over here, so that I can make a tangent out of this. This is famously a tangent times a secant. Derivative secant is, of course, secant x tangent x. That's no little example. That's a timeless derivative. Everybody knows that one. Derivative secant is secant times tangent. Okay. Of course, at the heart of it was this idea that when you bring down this power, bring it down, subtract 1, and then you got to do the stuff prime, giving you the secant tangent x. Super famous. Okay. Want to try another famous one? Cosecant. All right. Let's see if we can do the derivative of cosecant. That would be sine to the negative 1 of x. Yeah, see, that notation is kind of strange because you might think that I'm talking about arc sine, but I'm not. I'm talking about sine to the negative 1. And then I got to do the prime of that. Well, that would be negative 1 sine of x to the negative 2 times sine of x prime. That's the chain rule. I have stuff to the negative 1. Here, if I do it on the side, if I had x to the negative 1, it would be just negative 1 x to the negative 2, and that would be fine if it was just x. But if it's something other than x, you got to add the x prime. That's what the chain rule is telling you. So this is exactly the same thing we did on the previous example. This gives you a grand total of negative 1 all over sine square of x. The derivative of sine would be cosine of x, and you can spread this sign on the bottom around. give this one a sine of x, give the other one a sine of x, and what do you have here? The incredibly famous, the timeless derivative. The derivative of cosecant is negative cosecant x cotangent x. Everyone knows that one. Okay? Anybody who is somebody knows that one. Timeless. I told you everything on that book we can do using the chain rule. You don't believe me? Try this one. Oh, this one's good. I don't know if I want to try that one yet. Try this one. Oh, that one's good. I don't know if I want to try that one yet. I'm just playing. All right, let's see how you do that one. So here's a famous way. This is again a time. This is no chump of a derivative. This is no low-life derivative. This is a timeless derivative, one of the nicest ones. So watch how it gets delivered by the good old chain rule. I'm going to be using for that. I'm going to get this out of the way because I need a little bit more room. So let's clear that. Let me give you a little ingredients. The ingredients that I'm going to use the ln one. ln of stuff, right? You guys like stars, or I use a for stuff. If I had to take the derivative of ln of a, it would be 1 over a. If it was x, you'd be done, but if it's anything other than x, if the prime is with respect to anything other than that, you usually don't go with a prime on that. That's the chain rule part. Clear? This is one of the key ingredients that we'll need. And that should do it. That's all we need. Let me see, where was it? Oh my goodness, I lost it. I'll put it here. Anyway, so we want to find the derivative of e to the x. Here's something famous. ln of e to the x. That's something famous. Yes, I've seen that. If these are inverse functions of each other, ln e to the x would cancel and just give you x, right? Everyone knows that. Well, then dx of that would be dx of that. Slap a ddx on both sides. Why not? That would give you the following line. That would leave you that would give you that dx with the derivative of x with respect to x is 1. That was one of the famous properties. The derivative of x is 1. The derivative of ln of stuff. That's what I'm going to use here. The ingredient, it would be 1 over e to the x times e to the x prime, or I'm using the ddx, so I'll keep the ddx notation going. Let's erase this little baby here. Right? Again, the derivative of ln of stuff would be 1 over stuff times the derivative of the stuff. So dx of e to the x, I'm going to multiply both sides by, on the top equation, I'm going to multiply that side by e to the x and this side by e to the x. So I get rid of that one right there. So these two would cancel. Right there. They're gone. And that would just leave you with e to the x. And it leaves you with the amazing statement that ddx of e to the x is equal to e to the x. One of the few and privileged functions that turn out to be their very, very, very own derivative. The derivative of e to the x is, my friends, e to the x. Timeless. Super, super timeless. I told you. 100 years from now, when you're old and people tell you, hey, did you ever take calculus? You say, yeah, I took calculus. And they ask you, what's the derivative of e to the x? And you say, what? I can't. E to the x? And yes, you're right. You just have to repeat e to the x. That is its own derivative. It doesn't happen very often, only for a couple functions. One of the functions is e to the x. The derivative of e to the x is e to the x. Yeah, maybe I should give you as a homework question. What is the other function that is its own derivative? Alright, let's do the quotient rule. Quotient rule is, again, super, super famous. Nowhere near as famous as the chain rule. Nowhere near as powerful, but still something we really, really need to do. If you wanted to take the derivative of that, here's one way to look at it. G over f. Sometimes I get tired of writing the x's there, so don't worry about that. This is the same thing as g times f to the negative 1. where that -1 is not the inverse but the exponent prime. And so I could use the product rule. Remember with the product rule? The product rule said if you have the product of two things, well, you just write them all over again. You go f -1 plus g times f -1, and all you do is on the first one you do the derivative here, on the next one you do the derivative there. Remember that? That's called the product rule, and that's okay. That's not a big deal. So that would give you g prime times f to the -1, where again -1 means exponent, means on the bottom, plus g. Okay, this one gets a little interesting. I have blah to the -1, and keep in mind, if I had x to the -1 and I had to take the derivative, that would be -1 x to the -2, and you might be done if it was just plain x. But if it's not, you got to do the x prime. This is the chain rule. So I'm going to do that right here on f. So that would give you -1 times f to the -2 times f prime. That's no more, no less than chain rule. Giving you g prime f, giving you g prime all over f. So this f to the -1 means f on the bottom, plus g, actually minus g, because I have a minus here, and I have an f prime there, and I have an f square on the bottom. So I put the f square on the bottom. That's what it would be. Of course, we can get a common denominator. Why don't we get a common denominator? This looks like it has f squared. That just has a plain old f. So if I get slap an f on both the top and the bottom, that would give me the same denominator on both of these, f squared. So that would give me a total of g prime times f minus g times f prime all over f squared. This, my friends, this is super, super famous. This is the world-known, well, the world-known quotient rule. It tells you exactly how to take the derivative of a quotient. It says you take, oh, I don't know if you can see that. I should have said something. It takes to take the derivative. It tells you to take the derivative of the quotient. You do exactly what you would expect. You take the derivative of the top times the bottom minus the bottom times the derivative of the top all over the bottom square. I'm kidding. You wouldn't expect that. It's crazy, huh? But that's exactly how it works. And behind the derivation of that was, of course, the famous product rule, first of all, and also the chain rule. Deliver the goods. You guys want to try that on an actual example? Super, super famous. The derivative of the top times the bottom minus the bottom. The derivative of the top times the bottom minus top times the derivative of the bottom all over the bottom square. Just like that. Let's try it. So suppose you have x squared all over sine x, and you wanted to take, you were feeling kind of crazy, you wanted to take the derivative of that. Here's how you do it. You take top times the bottom minus top times the bottom all over the bottom square. And of course you do a couple of derivatives. The derivative of the top times the bottom minus the top derivative of the bottom all over the bottom square. That's a good setup right there. That's perfect. This is no more no less than quotient rule. So that becomes equal to 2x sine x minus x squared cosine x. I'm using famous ideas. The root of sine is cosine all over sine squared of x. See that? Amazing, huh? It's amazing how far we've come in just 1 week's worth of work. We're doing derivatives all over the place. Every single function that you can think of, we can find a derivative of with just these few tools that we develop over a couple of days. You guys want to do one more timeless? Timeless. I love timeless ideas. Let me clone this page so I could do more timeless. So let me do, for example, tangent. The derivative of tangent x, that's got to be timeless. The derivative of tangent is not so accessible unless you write it, for example, in terms of something that we already know, cosine x. And why is that a nice thing to do? Because now we've got the famous quotient rule. Quotient rule says you take the derivative of the top times the bottom minus the top times the bottom all over the bottom squared. And you got to do a couple derivatives, right? The derivative of the top times the bottom minus the other derivative, just like that. That's a good setup right there for quotient rule. And that becomes, let me think, the derivative of sine. Oh, this is duck soup. The derivative of sine is cosine. Cosine x times cosine x minus sine x. The derivative of cosine would be sine, negative sine, so that would make that one a plus, all over cosine squared x. Oh no, we didn't. What else? What's happening here? That becomes cosine squared sine squared, cosine squared x plus sine squared x all over cosine squared x. I wonder what this becomes. Sine squared x plus cosine squared x. That's super famous. You can exchange that for a 1. That's one of the famous identities. Sine squared plus cosine squared of the same angle is 1. And this, of course, 1 over cosine squared is famously known as secant squared x for a timeless derivative. The derivative of tangent is, of course, secant squared. Anybody who is somebody's done that. Okay? Timeless derivatives. I'm telling you, now you have the power to do everything in that book. I'm wondering if I should take it up a notch or two or stop there. What do you guys think? Maybe give you guys an option, like the Pilates class. Yeah, this is option time. Option time. If you guys are okay with that, you should stop the tape now and go to the homework. You need to practice a lot. I mean, this stuff you don't learn just by watching. Even if all your life you've been good at math and you can just get by without doing much homework, pretty soon that may not be the case. So I encourage you guys to do all the homework that you can get your hands on, so you can become super good at derivatives. Anyway, so a lot of you guys can stop here. Some of you fearless souls, people with big souls, stick around. Let's do the arctangent. Y is equal to tan inverse of x, where here I mean the composition inverse. Here, maybe I should write it this way. What do you guys think about this? What if we write it this way? Y is equal to arc. Yeah, I think this is better notation, man. People should write it this way. Alright, and I want to know, what is the derivative, dy dx? So, so here's something I can do. I can say, hey, you know what? If this is true, that means that tangent of y, the angle y, would be equal to x. That's exactly what this line means. It means that y is the angle such that when you take the tangent of it, you get the ratio x. Yeah? And then I'm going to play some game here. Fearless game. Slap a d dx on both sides. D dx on both sides. D dx. And what's the derivative of tangent? Well, we just figured that out, right? The derivative of tangent is secant squared of y. But if you stop there, you're going to get it wrong. The whole lesson today has been about chain rule. So what do you have to add at the end? Tangent of stuff. What's the derivative of tangent of stuff? It would be secant square of stuff times the stuff prime. You got to do that. And that's equal to d dx of x. Well, that's pretty easy. The derivative of x with respect to x, this matches. There's no stuff there. All there is x. So that piece is equal to 1. So wait a minute. Secant squared of y dy dx is equal to 1. This is starting to look really good, because dy dx is exactly what I was after. When I put my y equals arctan x, what I really set out to do at the beginning of the problem is I want to find dy dx. That's what I want, because this is my y. This is my function, f. When I get to this point, when I solve this, I will be done. It'll be yippee-ki-yay time. And I'm almost there, because I see that figure right here, dy dx. All I got to do is solve for it. Now you know that secant is 1 over cosine, right? So maybe it might help if I write it this like 1 over cosine y. Dy dx is equal to 1. Maybe I could slap a cosine on both sides. That would give me dy dx is equal to cosine square y. But wait, there's more. Whoa. Wait a minute. Let's go back. Let's backtrack our steps here. Tangent y was equal to x. What does that mean? What in the world does that mean? tangent of y was equal to x. I need to use that relationship to figure out cosine y, so I could plug it in here and be done. So I think I can draw a triangle and say, well, tangent is defined to be the ratio of opposite to adjacent. If this is my y, the opposite one is x to 1, right? Tangent y would be x over 1, and the hypotenuse would be the square root of x squared plus 1, using the Pythagorean theorem, right? That's kind of bad. That's not the kind of teacher I am. I'll draw a nicer one for you. If this is y, tangent of y is equal to x. So this is x, this is 1. That's opposite to adjacent. And then this one has to be, by using Pythagoras, x squared plus 1, square root. Oh, but now I can look at that and I can tell you what cosine y is. Cosine y would be equal to 1 over the square root of x squared plus 1, yeah? It's a ratio of adjacent to hypotenuse. And I got that from the original relationship. From that I get the triangle, from the triangle I get the sides, from the sides I get the cosine. And now I'm looking good because, well, look at this. I do look good no matter what. But now I'm looking good because cosine y is 1 over x, square root of x squared plus 1. And then when I square it, I'm going to get that square root's going to go. So therefore I get my conclusion here. dy dx is equal to 1 over, or cosine squares, which would be 1 over x squared plus 1. Yippee-ki-yay. Super famous. Timeless integral. Or no, sorry, timeless derivative. I'm getting like 3 months ahead of us. Timeless derivative, the derivative of arctangent. Here, I'll substitute the y here, so you can see. Let me erase this. This is better than, I can erase all this because you could just rewind the tape. But what I've done here is this says exactly the same thing as d dx of arctangent of x, that's my y, is equal to 1 over x squared plus 1. Yippee-ki-yay. Take us home. Alright, peace guys. Do the homework. See you guys here next time.